welcome to this Agilent Technologies recorded webcast. We hope you find this webcast both interesting and valuable. If after viewing this recording you're interested in more, go to Agilent TM Webcast YouTube channel for more recordings, or sign up for one of our upcoming live sessions at www.agilent.com/find/web_seminars. Now, over to the presenter.
And welcome, everybody. Thanks for dialing into this webcast. As you pointed out, I'm going to talk about polarization challenges in 40 and 100 V network upgrades. And where I'm coming from is actually we founded Adaptive Photonics in 2002, and since then I'm working on polarization solutions. And since 2007, we are part of Agilent now, and we sort of contributed our products to the Agilent portfolio. And so I'm quite a while in this polarization area, and somehow I have the feeling it's not getting less when we move to 100G. And 100 gigabit, I'm going to tell you why we think this. If I can move to the next slide. Okay, sorry for that. I'm going to talk about the things we are working on lately, and I selected 4 things out of this. One thing is called In-Situ PMD-measurement. In-Situ PMD-measurement allows you to measure PMD while a link is in service. That is a little different to what people normally do. Normally you have to turn off the link and then measure and then put it back in service. And so In-Situ PMD measurement allows you to characterize the PMD of a link while the link is running. So that's what I'm going to talk about. In this context, the term effective DDD, effective differential group delay, is popping up. So I'm going to explain you what's that about. And lately, when we talk with people about Polmux systems, in the area of 100 gigabit, it turns out that questions arise with respect to PDL. So I'm shortly address this topic because we did some work on that too. And finally, I'm going to talk about something which is puzzling us for maybe a couple of years already, that because people need to characterize the PMD tolerance of their transmission systems. And
sorry for interrupting, Harold. Would you mind speaking up a little bit louder? We've had some volume issues.
PMD tolerance testing is a topic which is keeps us busy for the last 2 years because there are no standards yet available for testing the PMD tolerance, even or in particular at second order PMD. And when it comes to dynamics, there seems to be a black hole that people are not really do not really know how to efficiently test the PMD tolerance of the systems. And so actually there are no agreed standards at the moment, and so we are trying to work together with our customers to find a good way to characterize the PMD tolerance of the optical receivers. So let's move on. When moving to 100 gigabit, we will probably see 3 paths people will take depending on the particular application. Only in the backbone network we will probably see the really fancy new modulation schemes. The shorter reach systems probably take some more pragmatic approach. I think I saw solutions like of course WDM systems where you just transmit over 4 wavelengths which are very far away from each other. The shorter the reach, the less important the fiber becomes. So people are taking that, just taking 4 fibers instead of multiplexing it to one single fiber. So what is actually what we are addressing more is the long haul systems. In the long haul systems, we will see polarization multiplexed signals which add up to 100 gigabit per second in one ITU channel. So what essentially is happening is in long-haul systems, the challenge is to transmit 100 gigabit over a 10 gigabit infrastructure. In those days, this 10 gig infrastructure has been installed with looking forward to 40 gig, so it's not that bad, but people did not really consider 100 gigabit at that time. So the challenge is to squeeze a 100 gigabit spectrum into maybe 50 gigabit channels. So you only have the 50 gigahertz bandwidth available, and you somehow have to compress the spectrum of your 100 gigabit signal into that. If you look at that, it's actually something very common. The wireless people are doing this for ages, and I don't know if we think back what we had, I don't know, maybe 10, 15 years ago, we used to transmit 56 kilobit over a 3 kilohertz phone channel. So that is exactly what's happening now in the optics, and it's actually quite thrilling to see that these kind of advanced modulation schemes are finally arriving in the optics. So compressing the bandwidth of a channel is nothing really new. You rather talk about symbol rate now instead of bit rate. So essentially what you're doing is you're keeping the symbol rate low, and you are coding more bits into one symbol. And if you take a look at the symbol rate, you will find that the symbol rate at 100 gigabit can be around maybe 27 giga symbols per second. And what goes with that is that due to the low symbol rate, you get a lot more tolerant against linear impairments like PMD, CD. And so that is what people see is a big advantage in the new 100 gigabit approaches. And so how to do this? So people will use multi-level codings. There are a bunch of possibilities you can use. It seems to be agreed that we probably will see polarization multiplexing, which is quite thrilling because people talking about this over the last 20 or 30 years, I don't know. But now finally I think we will see polarization multiplexing, and there will be a couple of challenges coming up if you transmit two signals in two polarization states. I'm going to address this a little later. But the polarization multiplexing will make compatible to the 50 gigahertz channel spacing. And so I think this is reason enough actually to do it. And I know that a lot of people are already developing and have products almost available. The very interesting thing is that people are developing coherent detectors at the moment. Everything is about coherent reception. And in general, that should be quite a hassle to have a laser diode at the receiver side. But it seems that the benefits are good enough that this can be justified. And so the coherent detection combined with polarization multiplexing and the new modulation formats are giving a very interesting performance features. And you will see a very high CD tolerance against chromatic dispersion, and PMD. So that is a development which is taking place, and it's just a question of time when it will be introduced. Some people are very aggressive in that and talk about maybe end of next year. Some people are saying, okay, we are just want to be prepared and let's see where the market moves, but I'm not doubting that this will come. So that would be an example of a modulator for PolMux, polarization multiplex signal. You have a light source, you have two modulators, and you essentially combine it using a polarization multiplexer. So this is going on the link, and and on the link will be more or less two polarization states at the same time, and you have to use a coherent receiver to analyze the signal again and to remove these two components back. So in terms of testing, we will probably see different kinds of test methods. The common DCA, which used to display an eye diagram, is not enough anymore. People are wanting to see the constellation diagrams, like here on the bottom right, constellation diagrams. But if you take the polarization as another parameter, then you need a third dimension. So some people draw these nice pictures like this. You duplicate the constellation diagram into some sort of toroid space, and which allows you to visualize what's happening on the link. So there will be a lot of new challenges coming up for analyzing these kinds of signals, because you don't have 0 or 1 anymore. You have the intensity and the optical phase and the optical polarization, which is quite thrilling, but of course you have to spend some time on how should we analyze this. And Agilent recently came up with the optical modulation analyzer for analyzing optical or modern optically modulated signals. You can see that this one is capable of showing you the constellation diagrams. It can look at spectral properties and can also, of course, look at eye diagrams. So I'm not going into that deep detail here in that, but this is a very powerful tool to analyze these newly modulated signals and gives you much more insight than just a simple DCA. But that would be one example of new test instrumentation which you will be needing for these new modulation schemes. So if we step back a little and see, I mean, what I just said is that 100 gigabit will be there, but it's not here yet. At the moment, what is deployed in the field is 40 gigabit and even 10 gigabit. I mean, it's not that 10 gigabit is dead, but 40 gigabit is sort of the high end at the moment, and it became pure and is deployed today. So this is state of the art. PMD, Polarization Mode Dispersion, is still a challenge, and it turns out that most systems I know include a PMD compensator or some sort of means for compensating the PMD of the link. My understanding is that this is optional, so my understanding also is that nobody really wants it in the system, so people try to avoid this because this is creating you some sort of how to say, it increases the probability that you will have some problems. So if possible, you want to avoid PMD compensation. So I think this is the reason why these questions here on the bottom arise. So what actually is the PMD tolerance of my particular receiver? I'm going to address this at the end of this talk. And another very practical question is, can I actually transmit this 40 gigabit signal over my particular deployed link? And turns out that customers actually coming to us and ask us, okay, how can we measure this? How can we measure this? And the scenario basically is you have a fully loaded 10 gigabit WDM link, and this link needs to be upgraded to 40G. The reason why it needs to be upgraded is because it's full, right? So you probably earn a lot of money with that, with a 10 gigabit traffic, and you have to increase the capacity. So and if PMD is a concern for you, then you want to measure this link, but what you don't want is to turn off this link just for doing this measurement. Because if you turn off all these, let's say, 40 or 80 channels, then this will cost you a lot of money. So as opposed to traditional PMD methods, PMD measurement methods, you want to have a PMD measurement solution which allows you to continue using this link while you're doing the measurement. And this is why we came up with the In-Situ PMD measurement. In-Situ PMD measurement allows you to measure the PMD, and you don't have to turn off the transmission. The idea basically is you ideally just plug in the in-situ test set to some of the monitoring ports of your EDFAs, and then you have access to the whole WDM spectrum, and the analysis is just taking place on that. So that is the basic idea. So I'm going to show you how that works at the moment. So the basic approach is we are using a polarization spectrometer. So what is that? You don't have to fully understand how that works. I mean, you can just remember that a PMD link is sort of manipulating the polarization state of your transmitted signal, and PMD is changing the spectral properties of your polarization state. So if you are using a tunable bandpass filter like we have here, we are scanning this over the signal, and we can scan this over the whole WDM signal actually, and we are observing the polarization state at the output of the filter. Then we get the polarization state as a function of wavelength. Polarization state as a function of wavelength, so that's why we call it polarization spectrometer. So we can just tap off some light, and we can take a look at the polarization state. And by looking at these polarization trajectories, we can measure a parameter called effective differential group delay. The effective differential group delay essentially is reflecting the instantaneous distortion level. I'm sure most of you know the differential group delay. Differential group delay is a parameter of the link. It describes the link. But effective differential group delay describes your signal. It describes how strongly your signal is affected by differential group delay. So that is really a measure for the distortion level of your signal, and it turns out that the PMD coefficient of the link, which most people are interested in, can be derived from this effective differential group delay. And this is what makes it a very powerful tool to characterize the PMD of your link, because essentially you end up with a PMD coefficient, which is a number which you can compare to other measurements too. So the result you get in the end is comparable to what you might have collected before in your traditional measurements. So just very briefly introducing how that works. So I told you we are measuring polarization trajectories. So we are measuring something like this here. You get a trace on the Poincare sphere, and it's essentially the effective differential group delay is the length of this trajectory. It's actually that easy. So you see that you can get different trajectories here. This trajectory is longer, and this is due to the input polarization state, and this is why we need to talk about effective differential group delay. The inherent property here is, if you take a look at the link has some certain differential group delay, and the link here has certain differential group delay, and depending on the input polarization, you are seeing this DGD or you are not seeing it. If you hit the principal states, then you wouldn't see any distortion, although there is DGD. So this is why we can't really measure the differential group delay, because sometimes we don't see it because the information is gone. We are seeing a very nice signal, although we have differential group delay on the link. So if you hit the principal state of the link, you will probably see a spot here as a function of wavelength. So it's actually not moving at all. But if your input polarization is far away from the principal state, you will see a longer trajectory, and then you will also see an increased effective differential group delay. So how does the effective differential group delay correlate with the signal quality? And therefore, we did experiments together with Alcatel-Lucent in Germany, and just for demonstration, we put some differential group delay on a link, and we changed the input polarization state. And changing the input polarization state will change your signal distortion. Sometimes you will hit the principal states, then your signal is nice, and sometimes you're far away, then your signal gets bad. And we used our In-Situ PMD analyzer to measure the effective DGD and recorded the bit error rate at the same time. So you are seeing that for low values of effective differential group delay, we end up here, and for higher levels, we end up here, in this area here. So essentially what you're seeing is that there is a correlation between the higher the effective differential group delay, the higher the distortion. So we have a very nice distortion meter here. And so essentially the effective differential group delay can range between 0 and the maximum level it can reach is the DGD of the link. This is what you are going to see in the reality. So now what to do with the effective DGD? It tells you how strong your signal is affected by PMD at this moment. This is sometimes very useful if you're questioning yourself, okay, I see a very bad bit error rate, and I think it's not due to CD or not due to anything else. So the remaining guess is always, oh, maybe it's PMD, but normally you can't measure this, and so it's normally an assumption. And using this kind of measurement, you can be either sure it's PMD or not. I mean, you just plug it in, and then you see the distortion level due to PMD, and then you can see either, okay, it's due to PMD or not, and if not due to PMD, you have to continue searching. So for debugging is a quite powerful tool, we found out. Now, if you do several measurements of the effective DGD, and you can do this either by taking different channels, or you just measure the effective DGD over time, let's say a couple of days or weeks, and then you will see the effective differential group delay has some statistic properties. Everybody knows, meanwhile, that the differential group delay seems to be Maxwell, or is Maxwell distributed. And the definition of the PMD coefficient is just the average value of the differential group delay. So people normally measure the differential group delay, and they are taking the average value and end up with a PMD coefficient. And you can do almost the same with the effective DGD. You take the effective DGD, and you find out that it's Rayleigh distributed. And once knowing this, you can just take the effective differential group delay here, take the average value, and divide it by 4 over pi. And you end up with the same number. So this is a very important for users, because they need to compare the measurement results to older results, and so you can really get comparable results, and this is helping you. So what I'm saying is that the effective differential group delay is just as good as measuring the differential group delay. So now a little more about the challenges of this method. We showed that this method is quite well for 40G channels. The 40 gigabit channels have a certain bandwidth. Normally they use very or a little advanced modulation schemes like DQPSK schemes, something like this. If you look at 10G signals, 10 gigabit signals are narrow, and they use simple modulation schemes like on-off keying or OK. And if you use on-off keying, you probably have a very strong carrier. So this actually makes it very difficult to analyze these signals using an optical tunable filter. And so what people are doing, if they want to do the in-situ measurement, they actually change the system a little. They replace a 10G transponder by a 40G transponder and use it as a stimulus. So, and this is a little disappointing. So, but actually, the use case sometimes is really that your 10 gigabit link, you want to upgrade to 40 gigabit, but you have to measure with 10 gigabit. Or it would be helpful to measure with 10 gigabit because your 10 gigabit system is running at this moment. So this is why we are continuing working on this measurement principle, and we adopted some heterodyne approach, which has been published in the past. Heterodyne measurement is done using a local oscillator at the receiver side. And what we are doing is we are selecting one WDM channel, and we're using one of our tunable lasers in combination with a polarization synthesizer and superimposing them on the photodiode. And by doing this, you get essentially the same information. This time you are not sweeping the laser or something. You are just doing the analysis on the in the electrical domain. You look at the RF spectrum, and you switch the polarization synthesizer to different polarization states. And we are using 6 different polarization states, and so one measurement consists of 6 RF spectra. And once doing this, you have enough information to reconstruct the SOP trajectory which you have at the input of the system. But this time you have a much higher resolution, optical resolution for this, and this allows you also to analyze narrowband signals like the 10 gigabit signals. So here's an example of a measurement result. On the left side, you are seeing that that the effective differential group delay is close to 0. There we coupled into a principal state of a DDD emulator. And on the right side, you see an effective DDD of approximately 9 picoseconds. This is pretty close to the maximum value we could see using emulator at 10 picoseconds. So that is just to give you an example of what we get. We get really the polarization states as a function of wavelength with a very high resolution. And so we are thinking this is a promising approach to go to in-situ PMD measurements at lower bit rates. And we think that this is going to be a very compelling solution for characterizing PMD tolerance of your 10G systems in order to upgrade it to 40G. So that was PMD. What about PDL now? And actually, why didn't people talk about PDL before? PDL, to my knowledge, is coming up now when you talk about the higher or better modulation schemes, which not necessarily include pole mux. Pole mux is surely a driver for having a concern about PDL. But also, if you look at PMD compensators, which are using the degree of polarization as a feedback, it turns out that you want to look at PDL problems and see if there's something you should consider. And so why is that? If you take a look at the pole mux signals are transmitting in 2 orthogonal polarization states. And now, most of you might know if you just put a polarizer into the path, you will probably see interference because components of the 2 signals are mixed together into one component, one polarization state. Now, PDL is not a polarizer, but PDL is a sort of bad polarizer because it is, when we talk about PDL, we probably talk about PDL levels between 0 and maybe 3 dB. And 3 dB is already quite a lot. It behaves like a bad polarizer. And so you are going to see that the 2 components are mixed together. And so what is the impact of a 100G signal where you mix the 2 orthogonal polarizations together? And generally, this is a linear distortion and should be, and the receiver should be able to compensate for it. But you have to design your receiver for that. You have to test it. So I think that we are going to see the need for tunable PDL sources, which allow you to deterministically move your PDL level to between maybe 0 and 4 or 5 dB. So you can actually stress your receivers using PDL. So that is one concern people have. PDL might be a problem with the new modulation schemes. PMD compensation at 40 gigabit might also be influenced by PDL. And in particular, if you use the degree of polarization as a feedback signal. The reason why people use degree of polarization is because you get a quite nice quality signal out of the DOP. The lower the DOP, the more your signal is impacted by PMD. DOP is also affected by noise, but this is just like an offset. So that if you are using a PMD compensator which optimizes the DOP, you probably try just to increase the DOP, and you will see that your signal normally gets better. So now, when you introduce PDL to the system, this is not quite true anymore. You will find that due to the polarizing properties of PDL, you can actually increase your DOP without making your signal better. You can also decrease the DOP without making it worse. So PDL is actually somehow influencing your error criterion, so you might want to find out if that is creating you any trouble in the real system. That is actually the reason why we looked a little into that. That is a measurement we did in our government-funded project. We are participating at the 100 gigabit Ethernet transport program in Germany, together with Alcatel-Lucent, and we introduced some sort of tunable PDL element which we developed into our system, and we put a polarization scrambler at the input, and we wanted to find out what actually is happening. And of course, we had some expectations, and it actually turns out that, of course, if you turn the PDL element to 0 dB, then you scramble and the DOP is not changing a lot. Once you increase the PDL levels, you will see that the PDL is creating some change in the degree of polarization. You see that although the PMD level or the PMD distortion is not changing, you see some changes in the degree of polarization. And it is plain to see that actually if you have a PMD compensator, the PMD compensator is trying to work against it and trying to optimize this. So that is something you want to understand if you have a PDL problem on your link, because this is probably influencing the capabilities of your PMD compensator. So PDL in combination with SOP scrambling is creating power fluctuations. It's actually not only power fluctuations, it's some sort of change in OS&R. You get a changing OS&R level because normally on the link you will have EDFAs which are clamping the power level. So normally what you will see at the end is that you have some breathing OS&R levels, which is also not very nice. You will see changing bit error rate penalties, and you will see the DOP variations, like I told you. And if it's a problem for you, depends if you have a PMD compensator or not. Okay. So I'm sure we will hear more about the PDL problems in the future, and it's going to be solved, I'm sure, but from our perspective, we think that there should be some more instrumentation for PDL also. The last topic I want to talk about is PMD-Tolerance-Testing. And this topic has been out there for quite a while, and people are doing PMD-Tolerance-Testing already. So um, for the 40 gigabit applications. But it turns out that this is still some sort of pain because there are no agreed standards yet on how to do PMD tolerance testing. How the receiver or the system vendors are expecting some sort of characterization, and the component vendors are having to agree to this or having to do these kinds of measurements. And I got some quotes from people saying, okay, we have our receiver, we have maybe 5 customers, and all 5 customers want different characterizing methods. So it seems that this is really a pain. And at that point, we are still talking just about the very basic characterization for first order and second order PMD. And since the receivers are now getting more intelligent and they have some adaptation algorithms, not only the receiver threshold, but also some sort of filters which needed to be adapted, you are going to see that the receivers will have some dynamic properties. They have response times, and these response times can be much slower than the bit rate is indicating. So we are not talking about picoseconds. We are talking about milliseconds at that point. And so that is clearly something you want to characterize, and we are still working on that and to see if there's a good way of doing that. And instead of doing this like people have done this before, they just introduce some maybe dynamic distortions, and they see if it works or not. So just like get a pass-fail. We are looking at what other technologies have done in that, and something you are pretty much familiar with, I suppose, is audio amplifiers. So what people did at that time with audio amplifiers is just you just look at the cutoff frequency of your audio amplifier. Cutoff frequency of the audio amplifier actually gives you a quite good measure for what you can do with it. So if your cutoff frequency is 3 kilohertz, it's suitable for telephoning, but surely not hi-fi. If you have an audio amplifier having a cutoff frequency around 20 kilohertz, then you probably should be quite satisfied if you want to use it for hi-fi. But the way you're characterizing these kinds of amplifiers is always the same. No matter what amplifier you have, you can just measure this characteristics, and then you're done. And after that, you are worrying about, okay, can I use it for this application or this application? So in this way, we have a standard way to characterize audio amplifiers. And so why not doing the same thing for dynamic properties of PMD? So the basic idea actually is you try to explore the limits of your system. You really try to find out at what point your system is showing some severe penalties. And a very helpful way to do this is you use a PMD source, which also allows you to create dynamic changes. So you really walk into the areas where it creates pain for your receiver. And you should just do this and see where you end up, and then you get some characteristics which you can share with other people. So, but I think there need to be standards in the future to do that, because otherwise you will end up with different people demanding different kind of measurements, and this is a pain for everyone. So our proposal is to use what we would call PMD test bed. One of the basic approaches is to get rid of the stochastic or the random scramblers in the setup. A lot of people using some sort of PMD source and polarization scrambler at the input, because you are dependent on input polarization, but very often it's difficult to adjust the input polarization. So one solution was just to use a polarization scrambler and wait until you get some statistics over the bit error rate. And so what we want to get rid of all the random behavior of the system. We want to propose a fully deterministic system which allows you to deterministically control the input polarization and also deterministically control the dynamics. And you can use our in-situ PMD measurement to verify what you are doing. And that's actually what we think how you should test the PMD tolerance of your system. So essentially, you combine a PMD source which is capable of creating a higher order PMD. You combine it with some polarization synthesizers for changing input polarization state and changing the output polarization state. And this gives you all handles you need to move to different stress patterns. You really want to stress your system and see where the limits are. So why am I saying second order? Second order PMD is around for also quite a while, and I think meanwhile it's commonly agreed that you have to measure the PMD tolerance also in the second order regime. So why do you have to do this? If we look at these diagrams here, on the x-axis there's first order, and the y-axis you have second order. So there might be receivers which have some certain tolerance to first order DG. This, then you walk on the x-axis here, you will see this. But they have some different, or they also have some sensitivity against second order PMD. Then you walk up in this diagram here. So maybe receiver A has this kind of behavior. You have diagonal lines, but there are also different receivers which just have no or almost no vulnerability against second order PMD. Then you will get sort of vertical lines here. And why is that important to you? There is a certain probability that first order DGD is appearing in the real link, and there's a certain probability that second order PMD you will see in the link. And if you have this combined probability, you know for each point in this diagram how often it will appear in a real link. So receiver A definitely has a different outage probability than receiver B. So, and that is something you want to know. I mean, the customers of the people who are buying the receivers want to know that, but of course, while you are developing this kind of receiver, you definitely want to know this. And interestingly, the 100 gigabit receivers have a lot of influence on this kind of behavior because most of the receiver properties are coming from some sort of FPGA or ASIC software. So now moving to 100 gigabit, you really have a handle on optimizing your receiver with respect to PMD tolerance. So I think this is a thrilling point here that you really can use these test and measurement approaches actually to optimize your receiver with respect to all these parameters. Just want to give you an example. You don't really have to go into deep detail in this diagram. That is an example of a measurement we did with a PMD compensator. And what you see here in the x-axis is the rotation speed of the polarization state. So you will probably see some similarity to the audio amplifier thing. And we really increased the rotation rate of the polarization state, and we saw that there's some point where you actually see the bit error rate going high because you are changing the polarization state. And so you really get a characteristic, the higher the speed, the higher the penalties are. And just to comment on this, one of these curves is for the rotation at the input, and the other curve is for rotation at the output. And you see that there are different maximum frequencies where you get increased penalty levels. So that is an interesting fact, and it's also important to know that about your system. So that is one example where this deterministic approach revealed some new insight into the properties of your system. And so we think actually this is the way to go, and you have to really also go into the second order domain to fully understand the PMD tolerance of your systems. So in conclusion, just want to summarize what I said before. Upgrading to 40G requires different instrumentation than upgrading to 100G. That seems to be pretty clear. 100G, you will also have to address PDL, these kinds of things. 40G, the problems are more practical, and 100G is not being deployed yet. 100G is going to be deployed in 1 or 2 years. So I'm sure there will be change demand on instrumentation. We think that in-situ PMD measurement is going to be needed when upgrading to 40G. It surely would be helpful to also measure 10G signals with the in-situ PMD measurement approach, and we are working on that. The 100G upgrade, as I said, is a little further out, but at the moment people are developing the algorithms for the receivers for compensating CD, PMD, whatever happens to your signal will be compensated. And we are offering for that the optical modulation analyzer, and we will be coming up with new products to address the upgrade to 100 gigabit. We think that people probably would need link emulators for showing that their receivers are tolerant to PMD, PDL, CD, whatever. At this moment, I think people are on the stage of using measured data and simulating using real measurement results, but simulating the effect of their receiver algorithms, because there are not too many people around having FPGA or an ASIC available for doing this. But I'm sure very soon we will see this. Interesting aspect is that once you are there, once you have your 100 gigabit receiver, the 100 gigabit receiver will tell you how much PMD, how much CD you would have on your link, because that's what the receiver needs to know to compensate for that. So once your system is up and running, and once you have installed your 100G system, you will probably get a monitoring readout from your receiver telling you the distortion parameters. So maybe for the 100G there's not really the need for in-situ PMD measurements anymore, but we definitely see this at this moment for 10G and 40G. Yeah, and maybe the last points here, we think that dynamic properties need to be addressed more in the future, because even if you have an ASIC, finding the parameters, depending on your algorithms, you will probably see some dynamic behavior which is orders of magnitude slower than the bit rate. So that also might be some optimization parameter you want to improve in order to see in order to have a high a quick response time to changes on the link. So I think I'm more or less done. If you have questions, I've seen that you already posed a couple of questions, so I would be open for that and open to answer them now.
Great. Thank you, Harold, for a great presentation. I will turn the floor over to Sven momentarily so that he can ask you any questions that he did receive. Again, if you have any questions during the next 10 minutes or so, please feel free to chat them. Also remember that there's a short feedback form that will pop up when you exit the WebEx. If you wouldn't mind taking a moment to fill it out, that would be great. Sven, do you have some questions for Harold?
Yes, we do have some questions. One of them I read several times. You already wrote in the chat that the presentation can be downloaded or obtained afterwards. There will be a follow-up, and the presentation material will be available afterwards. Okay, there have been some questions on some setup details. Harold, there was a question, what does EDFA stands for?
EDFA. Okay, that's sorry for that. I'm already quite long in this area. I thought this is EDFA is just erbium doped fiber amplifier. So the EDFAs are normally distributed along the link and to recover the power of your optical signal. So that is nothing. This is state of the art, and yeah. I mean that is really nothing special. EDFAs are just distributed along the link, and they can amplify your WDM signal and recover the power levels. So I don't know.
Okay.
Does that answer the question, or was the question going into some other direction?
I think so. There was a question, what is the required PMD emulation range if you want to, or can one say what the required emulation range would be to emulate a certain link with a given mean PMD like 10
okay. That's a good question. So what people are normally characterizing for an optical link is the average or the PMD coefficient. Let's say if the PMD coefficient is 10 picoseconds, that is telling you. That is basically telling you what kind of variations of the differential group delay you will see. So assume your link has 10 picoseconds PMD. Then if you take a look at your link now, you probably can see 20 picoseconds. You can sometimes see 30 picoseconds. 30 picoseconds is probably not so frequently. And the whole thing is distributed like a Maxwellian distribution. So most of the time you will see the 10 picoseconds, but there are few occasions where you see 30 picoseconds. And well, as a rule of thumb, people say you probably, in practical applications, you will see that three times the PMD coefficient. So 40 picoseconds you probably not see at all. 30 picoseconds you might see, but not very frequently. So if you want to emulate a 10 picosecond link, then your emulator should be capable of being able to be adjusted between 0 and 30 picoseconds. You can also adjust the second order. You can also derive the second order parameters from that. I don't have numbers for this at the moment. What I heard about the 100 gigabit receivers is that the PMD tolerance is actually quite increased compared to 40 gig systems. So people are talking about PMD tolerance of 50 picoseconds or even higher. So that would be quite interesting to see if this really turns out this way or not.
Do you know if there are any 100 gigabit receivers available already?
I know that a lot of people are developing them at the moment. I heard that there is actually, yesterday somebody told me, and I was not aware of that there seems to be a 100 gigabit link in service around New York Stock Market Exchange. That was a quite interesting thing. They seem to improve the latency time by using the 100 gigabit. So there must be something around, but it is in a very early stage at this moment.
Okay. How about this effective DGD you're measuring and been talking about? Is this considering second order effects?
Not at the moment. The second order is at that point, I think, not such a big issue because you are using the effective DGD to get the readout of the PMD coefficient. And once you know the PMD coefficient, you know that once you have the PMD coefficient, you have the full information about the first and second order statistics. So measuring the effective DGD is just a vehicle to get to the PMD coefficient. And On the other hand, it's also a way to measure your momentary distortions. So that in that area, that might be interesting to have to be able to measure second order. At the moment, this is not implemented yet. So the effective DFGD more or less focuses on first order distortions to get to the PMD coefficient in the end.
Okay. There were some test results being shown together with on slide 30. Have these measurements been done on live networks?
No, this has been a lab experiment. It has been a real transmission system, but it has been a lab experiment. It was not over an installed fiber link.
Okay. Okay. There have been some other questions like, well, some of them, I think it's almost 6 o'clock here. Oh, sorry, it's some other time on your place. I think we will have to answer some questions as follow-up. I'm scanning the list, whether we have something we can answer in short.
I mean, you can just send me an email and write your questions in an email. I would be happy to answer them as quickly as I can.
And I will be sure, we'll send everyone an email after the presentation with the presentation material and the on-demand URL. And I will include both Sven and Harold's email addresses if you want to ask a question directly.
Okay. Yeah, that sounds good.
Yeah.
So whenever you feel like you want to put a message, just send me an email and I'll get back to you.
Thank you for watching this Agilent Technologies webcast. For more recorded webcasts, subscribe to our Agilent TM webcast YouTube channel. All of our webcasts are held live. Interact with our Agilent experts in the live Q&A sessions and gain access to Agilent materials. To view our upcoming live webcasts and to sign up for free, go to our website, www.agilent.com/find/web_seminar.